Interpretations of the definite integral. So much like we did for derivatives, we need to ensure that we understand what the units are going to be when we find the definite integral of a function that represents a rate. So the notation in units for the definite integral. The units of measurement for any integral from a to b f of x dx is the product of the units for f of x, so the units of your function, times your independent units, or the units for x, so the units that show up on the variable that happens to be on the bounds. So remember where this comes from. We're getting our definite integral because we're looking at the sum of all these little rectangles. Well, to get the area of a rectangle, we were doing the width times the height. The width was giving us our independent units, and the height was giving us the units of f of x. So we need to multiply those two units together to get the units of our answer. So if for some reason f of x and your independent variable are going to be the same in units, then you end up with square units. So for example, if one is in centimeters and the other one is in centimeters, you're going to end up with centimeters squared. Now, this is a rare case, but it's the alternative that we usually encounter. So if the units of your function are something per something, so c per d, and the units of your independent variable are whatever d is, which is usually the case, then the integral results in just the units c. So what that means is usually your function has a rate, and usually the bottom of that rate cancels out. So for example, if your rate is in feet per minute, and then your time is in minutes, that means your answer is going to be in feet. So let's look at some problems and start practicing with our units, and also trying to reason through some information we may have about the function itself. Example 1. A bacteria colony initially has a population of 14 million bacteria. Suppose that t hours later, the population is growing at a rate of f of t equals 2 to the t million bacteria per hour. Part A. Give a definite integral that represents the total change in bacteria population during the time from t equals 0 to t equals 2. So the definite integral is going to go from 0 to 2 because those are our independent values that we were told here. And we're going to integrate the rate at which our population is changing. Since it's 2 to the t, this will be dt. So our definite integral looks like this. This represents the total change in the bacteria population during that time. Now, part B wants you to actually find the population at time equals 2. This is a subtle difference between what we've been doing before, which is finding the change in population. So let's see how this makes a difference. So if we want to find the population at time 2, the first thing we need to do is find how much the population changed. So if we calculate this integral from 0 to 2 and we plug that in, we're going to get 4.328. But again, that doesn't tell me the population at time equals 2. That tells me how much the function has changed between time equals 0 and time equals 2. However, if I go back to my original problem, I see that I initially had 14 million bacteria. So that means if I had 14 million bacteria and then I changed by 4.328 million bacteria, then I can add those together to find out my population at time equals 2. Let's make sure the units match up before we add those together. So 2 to the t was in million bacteria per hour, and time was going to be in hours. So the hours units would cancel, and so this 4.328 does represent million bacteria. So we don't have to do any conversions to add it to our initial amount. So the population at time equals 2 is 14 plus 3.28, which will give us 18.328 million bacteria. So two new things happened here. First, we had to be more conscientious about the units. We had to make sure we understood what the units of the integral were and that they matched the units of anything we wanted to combine them with. The second piece is that we had information about the original function, and we had to figure out how to use it. For right now, we're going to reason through how any initial information will apply to what we're doing. In the next section, we'll make it more formal mathematically on how we define initial information. But let's do a couple more problems. Example 2. Suppose that C of t represents dollars per day to heat your home, where t is in time measured in days, and t equals 0 corresponds to January 1st, 2018. We want to interpret what the integral from 0 to 90 of C of t dt represents. So notice here what our units are. C of t is in dollars per day. So dollars per day. Now our time, or our independent variable, is also going to be in days here, just like the previous problem. So the days units are going to cancel. So whatever I get on this other side is going to be in dollars. And I know here we're talking about the cost, right, in dollars per day. So what this represents, we have to bring in the numbers that are here on the bounds. So this is going to be the total cost, or the total amount of money, you could say, or the total amount of dollars to heat your home during the first 90 days of 2018. So what are the key parts of this sentence? What are the things you want to make sure you have in your sentence? So we want to talk about this 90 days, or you could talk about from day 0 to day 90. You could say something like, roughly the first 3 months, but you need to talk about this time span because that's when it's happening. And then on the other side, we said that once we find this number, it's going to represent the amount of money. So I'm calling that total cost, but you could say something like, the total amount of dollars you spend, or money, the total amount of money you spend to heat your home. But what's important is that we're finding the units of the definite integral here, and we're also including the units of the independent variable. So that's our sentence, and let's try another. Example 3. Water is pumped out of a holding tank at a rate of 5 minus 4e to the negative 0.15 t liters per minute. So our rate is in liters per minute, where t is in minutes since the pump started. If the holding tank contains 1,000 liters of water when the pump is started, how much water does it hold 1 hour later? So there's a couple things about this problem that we need to be careful about. However, we have a general sense that the first thing we want to do is find out exactly how much water was pumped out, which we can do by finding the definite integral of our rate. So here we're going to find the definite integral of 5 minus 4e to the negative 0.15 t dt. So I want to remind you that my rate is in liters per minute, and time is in minutes. So whatever number I get is going to be in liters. It's telling me how much is being pumped out. Now, one of the places I need to be really careful is the question asks, how much water does it hold 1 hour later? But we said that time is in minutes. So whatever units your independent variable is in, that's what has to go on the integral bounds. So that means I need to think about how 1 hour is related to minutes. So I'm going to do this as 0 to 60, because again, this has to be in minutes since t was defined in minutes. So now I have this integral, and if I plug it all into my calculator, I'm going to get 273.34. And I said before that it's liters per minute times minutes, so this is going to be 273.34 liters. Now, we know that the holding tank initially contains 1,000 liters. In a previous problem, we added the amount from the definite integral to the initial value. However, we have to be careful here because we're talking about water being pumped out. So if that is the amount of water being pumped out of the tank, we actually have to subtract this number from 1,000. So normally, if our original function is decreasing, when we find our definite integral, we would get a negative number. But here, we have to use the words to understand what's happening in the whole scenario. So in this particular case, even though our function's decreasing, the way it's worded, we have to be careful and understand that we have to subtract it off, even though we got a positive outcome here, because the outcome is how much we pumped out. So we're going to do 1,000 minus 273.34. We're going to double check real quick, but these are both in liters, so we don't have to do any sort of conversion here. So 1,000 minus the 273.34 will give you 726.67 liters. So that's how much remains 1 hour later, because again, we've pumped out approximately 273 in liters. Let's look at another. Example 4. The function f of t gives a number of gallons of fuel used per minute, so gallons of fuel per minute, by a jet plane t minutes into a flight. The integral 0 to 30 of f of t dt represents, so again, we're interpreting what the integral means. So we need to consider the numbers on the bounds. So that's going to be the independent units. So that's time in minutes. So we're talking about what happens during the first 30 minutes of a flight. Now, my function has the units of gallons of fuel per minute times my independent variable of minutes. So when I take this integral, the result is going to be gallons of fuel. So just the gallons part. So if I was going to put together a sentence to talk about what this definite integral means, I would say something like the number of gallons of fuel used during the first 30 minutes, so that was our independent numbers over here, of a flight. So again, there's lots of sentences that are right, but we want to make sure we've included that we're looking at the first 30 minutes and that we're talking about the number of gallons of fuel that were used. So as long as those two pieces are in your sentence, then you're good to go. Let's look at another example. Example 5. The rates of growth of the population of 2 species of plants measured in new plants per year are shown in the graph below. Assume that the populations of the 2 species are equal at time equals 0. Part A. Which population is larger after 1 year and after 2 years? So let's start by looking at what's happening after 1 year. So after 1 year, we're looking at the area under the curve for these 2 species. So the area under the curve for species 2 is the area that's right here. And then the area under the curve for species 1 is going to be this whole area here. So we can see that there's more area under species 1 than under species 2, which means that we've grown more new plants for species 1 during that first year. So after 1 year, species 1 is bigger. However, if we look at what's going on after 2 years, we can see that what happens is that species 2 starts growing a lot more rapidly, and then species 1 doesn't grow quite as fast. So what we probably want to do is we want to approximate the area of each of these to get a sense of how big they are. So for species 1, it looks like we can draw in a little triangle here to approximate that area. So that area, I'm going to come up over here. 1/2 base times height. My base is 2 years long. And now my height, I'm going to say that's roughly 2250. So that's halfway between 1500 and 3000. It's right about there. So when we crunch that number, we're going to get approximately 2250. And then for species 2, I'm going to do something similar where I'm going to approximate this using a triangle. So here, the area under this curve, we're going to do 1/2 base. Now my height is quite a bit higher than it was for our first species, so I'm going to approximate that to be approximately 3,900. It's a little bit above the halfway point, which is 3,750, so partially between 3,750 and 4,500. You could call that 4,000, but what really matters here is any estimate you get between 3,750 and 4,500 is going to give you a result that's larger than what we got for species 1. So after 2 years, species 2 is going to be larger because, again, there's more area under the curve of species 2 at time equals 2 than under species 1. So part B wants to know, how much does the population of species 1 increase during the first 2 years? Well, we actually found that when we were comparing. So during that first 2 years, it increased by 2250 because that was our approximation of the area under the species 1 curve. So again, if you want to compare how big 2 species are or 2 populations, you're looking at the area under the rate curve and you're trying to determine which area is larger. Sometimes it's really obvious and you don't have to do any calculations, but sometimes it's better to actually get a rough estimate of what it is to make that kind of comparison. So let's look at an application of this that's really important in the medical field. Bioavailability of drugs. So in pharmacology, the definite integral is used to measure the overall exposure of a person to a drug during the course of a treatment. So this is what's called the bioavailability of the drug. So as you can imagine, if you're giving someone a drug where you want to minimize exposure, say you're doing radiation treatment or something where whatever you're exposing them to is not great for their overall well-being, but targeted to help one specific part, you want to keep the bioavailability down. So the total exposure of a drug is going to be equal to the area under the drug concentration curve. So this graph should look familiar because we worked with it in an earlier section, because this represents a surge function. So when we look at the area under a surge function, we can calculate how exposed someone has become to the drug. Now, like I said, not all drugs are troublesome. There's some drugs that exposure to the ingredients is not a big deal, but you can think about some cases where you'd want to minimize the exposure to certain ingredients. So let's look at just a couple quick examples of how this is used and what sort of information we can get by looking at area under the curve and comparing different types of functions here. Example 6. 2 drugs are given to a patient and their concentrations are measured over time. Which drug was absorbed most rapidly? So the way that we figure out absorption is we want to figure out, 1, which drug peaks the fastest. That means it's reached its maximum concentration. But we also want to look at when these drugs actually finish running their course and get out of the body. So in this case, we can see that drug A reaches its peak faster, and then it also finishes its own course faster. So it leaves the body, it gets back down to 0. So that means that this drug was metabolized more quickly than drug B. It took less time to peak and get out of the body than drug B did, based on the shape of this graph, which is the rate at which the concentration is changing. So in this case, it's going to be drug A. So again, if you're looking for when drugs are absorbed most rapidly, you're looking first for the peak, and then if the peaks are different, then you want to see which one came first. So here A came first, so it was absorbed most rapidly. If, however, you're in a scenario where the peaks are the same, then you want to see which one gets out of the body first. In this case, drug A also gets out of the body first, so it qualifies for both conditions. But we look at the peak first, and then if you can't tell which one peaked first or if they're the same, then you look at which one leaves the body first. Let's look at another example. Example 7. 2 products are being tested for pain relief. The graphs of both products are given below. Use the graphs to determine which drug works the fastest and which drug has the largest bioavailability or overall exposure. So which drug works fastest? So again, that has to do with absorption. Which one is absorbed the most rapidly? Which one peaks first and hits its maximum concentration? Because that one's going to be working the fastest. So for this part, we can see that product A reaches its maximum before product B, which means it's working faster and being metabolized faster. So product A is going to work the fastest. Now, the second part is which drug has the largest bioavailability or overall exposure. So what you'll notice is because drug A peaked so fast and got out of the body so fast that the area under the drug A curve is pretty small compared to what's happening with drug B. So drug B has a lot more area under the curve. So the largest bioavailability is going to be product B. So depending on what the ingredients are of this particular drug, we may have concerns about how much exposure we have because of product B. Because it stays in the system longer, you're exposed longer, and the area under that curve is much larger than drug A.